All right, this is the 4.1, 4.2 extra practice worksheet. So we've been talking about Riemann sums and antiderivatives for the past couple of days. We're just going to practice some of those skills. Pay attention to the directions here too. So if you're being asked to find the general solution of a differential equation, if these are given as f prime of x, what they're asking us to find is f of x. General solution means there should be a plus c in all of my answers. If these said dy dx, I would be looking for the y equals equation. So I'm going to start off by saying f of x should equal whatever the integral of 1 minus 6x dx is. So using the integration, the integration rules that we learned, integral of 1 is x, integral of 6 minus 6x is minus 6x squared over 2, and then we add c, and we can simplify this a little bit. So f of x is equal to x minus 3x squared plus c. Simplification is not required, but we're usually doing something else with f of x, so it's good to simplify. For the second one, same idea. F of x, the general solution to this differential equation, should equal the integral of 3 cosine x plus 5x squared. This is in parentheses, by the way, because integration is set up as integral of a function times dx, which is like the width, that tiny little width of the rectangle times the height of the rectangle. All right, the integral of cosine is sine, so 3 sine x. Integral of 5x squared will be plus 5x to the third over 3 plus c. Since this doesn't simplify, I'm not going to rewrite it just to put an f of x in front. I already have that over here. All right, third example, f of x is equal to the integral of 1 plus, I'm going to write this as its exponent form. This is x to the 4/5. The type of root is the denominator. So the integral of 1 is x. The integral of x to the 4/5, we're adding 1 to the exponent. So add 5 over 5, you get x to the 9 over 5. And you would be dividing by 9 over 5. But we would want to simplify this as well. So x plus dividing by 9/5 is the same as multiplying by 5/9. So that's my final f of x. All right. So find f of x. That's different than find the general solution. All of these answers had plus c, meaning any vertical shift of these graphs would be a solution. This is find the specific f of x that fits this f prime and has this point on the graph. So this means find c. So first you have to find f of x, just like we were doing. So first integrate to get the f of x general solution. So it's the integral of 8x cubed plus 12x plus 3 dx. Make sure you're writing your dx. If you don't do that, you don't get credit for the integral, for setting it up correctly. So this becomes 8x to the 4th over 4, so that's 2x to the 4th, plus 12x squared over 2, so plus 6x squared, plus 3x plus c. And so that's f of x, the general solution. Now you need to use this ordered pair, plug in 1 for x and 6 for the y coordinate. So 6 is equal to 2 times 1 plus 6 times 1 plus 3 times 1 plus c. So over here, this adds up to 11. Solving for c, I get negative 5. And so they want the f of x. So f of x, the one solution, now that I have a specific point that has to be on the graph, is 2x to the 4th plus 6x squared plus 3x minus 5. I can check my work. I can make sure that the point 1,6 is on this graph if I had time. I can take the derivative of this and make sure I get the f prime that they gave me. So there are ways to check. All right, same thing for the next one. So let's integrate to get the general solution first. With integrals of trig expressions, it takes a little bit of studying or at least thinking about, sine x is the derivative of what, cosine is the derivative of what to get to that place. That's kind of what I have in my head. So sine is not the derivative of cosine, it's the derivative of negative cosine. So this is negative 5 cosine x. And I'm talking about derivatives because go back and if you're not sure on this, whatever you wrote down, take the derivative of this. Do you get 5 sine x? Same thing here. This is plus 3 sine x. Because take the derivative of this. Do you get 3 cosine x? Yes. Let's see. All right, now we need to plug in 0, 4. So 4 is equal to negative 5 cosine of 0 plus 3 sine of 0 plus c. Cosine of 0 is 1. Sine of 0 is 0. So this is just 4 equals negative 5 plus c. So c equals 9. And then writing the f of x. So f of x is negative 5 cosine x plus 3 sine x plus 9. Remember, if you're looking for a multiple choice answer, it's pretty likely they would use the commutative property and switch these terms around just to not have the negative out front. So just be on the lookout for that. All right, and then this third example gives me the second derivative, and I have information about both the original f of x and f prime. So if I have the second derivative, I have to find the first derivative equation first. That would be the general solution to the second derivative equation. So we have to take it a couple of steps, or just one step at a time, I should say. So f prime x, this is going to be 20x to the fourth over 4. So that's 5x to the fourth minus 10x plus c. And you don't want to integrate again right away. You want to find c. So make sure you choose the correct point. F prime of 1 is negative 5. So negative 5 equals 5 times 1 minus 10 times 1 plus c. So this is 5 minus 10 is negative 5. So if I add 5 over, I get c equals 0. So on this problem, I mean, I guess when c equals 0, that sort of allows you to get away with forgetting about finding c. But on an AP test, you would be getting credit for showing that you calculated c. They always say like uses the given value or something to find c. Okay, so now I want to find f of x. And that's the integral of f prime of x. So the integral of 5x to the fourth minus 10x, and c was 0, dx. Right, so this is 5x to the fifth over 5 minus 10x squared over 2. And I don't want to use plus c again. I already did that, so pick another letter. I'm going to say plus d. And now I want to use the other condition that they gave me. So f of x is 1 when x equals 1. So 1 equals negative 4 plus d, so d equals 5. All right, so f of x is equal to x to the fifth minus 5x squared plus 5. All right, next section, evaluate the indefinite integrals. So we're back to indefinite integrals. We should have plus c's in our answers, and we're just integrating. So I'm just going to go ahead and say equals. I don't need to set anything up. Excuse me. 5x to the fifth over 5 is x to the fifth minus 2x to the third over 3 plus 3x plus c. Before you start in on the next one, we only have rules right now for individual terms. We don't have right now we don't have like a quotient rule for integrals or anything. So remember, if you're dividing by a monomial, it's easier anyway to divide each part. So rewrite the integral first. This is actually 6x to the third minus x dx. So simplify the integrand, which is the expression in here, and it makes it a lot easier to work with. So 6x to the fourth over 4 minus x squared over 2 plus c. And I like to reduce my fractions. Not required, but encouraged, I would say. So that's my final antiderivative. Okay, now this one, you could try to go a few ways with this. You hopefully, from your pre-calculus days, are looking at these and saying, these are rearranged Pythagorean identities. Remember, we know that sine squared theta plus cosine squared theta equals 1. That one should be like burned into your memory. If you rearrange to solve for either sine squared or cosine squared, you get each of these expressions. But you do have to be careful of this, because if you switch this, so 1 minus cosine squared is sine squared. 1 minus sine squared is cosine squared. This seems like you're kind of on the right track and we're doing something here, right? This is tangent squared. But remember, we don't have a rule for how to integrate tangent squared. Tangent squared is not the derivative of any of the 6 trig functions. If it said secant squared, that would be equal to tangent, the antiderivative. But tangent squared is nothing. So we don't want to go sine squared over cosine squared. So what else could we do? Well, look back to part B. I do have a fraction here. So what if I just change the denominator? So I have just a single term in the denominator, because maybe division will help me out here. So if I keep it 1 minus cosine squared on the top divided by cosine squared on the bottom, now I can do that division thing again. 1 over cosine squared is secant squared minus cosine squared over cosine squared. So now we can integrate, because we do know the integral of secant squared, that's tangent theta. And remember, if you get confused on your trig, whatever you just wrote down for the antiderivative, take the derivative of that and make sure that you get secant squared. And then the derivative of minus 1 is minus theta. Theta is our variable in this problem, plus c. So sometimes with trig, you have to work it a couple of ways until you get something that actually works when you're working with identities. All right, next section. Given f of x is 5 over x on this interval, find a lower sum with 3 equal subintervals. So I can start by establishing delta x. It's 5 minus 2, b minus a, over the number of subintervals. 3 over 3 is 1, so that's nice. Now, it says lower sum. It doesn't say left or right. So we have to figure that out. And how do you determine that? You need to look at what the graph is doing on this interval. Is it increasing or decreasing? So I just think, okay, if I plug in 2, I get 5 over 2, which is 2.5. If I plug in 5, I get 1, which is lower. So this graph is decreasing on this interval. So which one's going to be the lower sum? Well, think about this. You're splitting this into 3 sections. If I do a left sum, all the rectangles are going to be a little bit outside of that curve. If I do a right sum, all of the rectangles are going to have a little bit of space left underneath. So it's a right sum because f of x is decreasing. So it matters what the function is doing, whether you choose left or right, if they just tell you lower or upper. All right, so this would be the integral from 2 to 5 of 5 over x dx, and we're approximating it. So we're saying it should be equal to delta x times, let's see, f of 3 plus delta x times f of 4 plus delta x times f of 5. So delta x is just 1, so I'm going to keep that out in front. And I'm just going to write f of 3 plus f of 4 plus f of 5. You can show those numbers plugged in if you want. Also, I'm going to go ahead and use a calculator for this, so I've got Desmos up here. So type in f of x. I mean, you could just type this in by hand. Again, it's not that hard, but I just want to show you this. So I can type in f of x. And then down here, I don't really need the 1, so I can just say f of 3 plus f of 4 plus f of 5. Now, this is the decimal answer. If you want it to be a fraction, click this. I kind of like the decimal answer, especially if they're having me do a few. I can compare what's higher, what's lower. So I'm going to keep it as 3.917. All right, so that's our upper sum. Find a midpoint sum with 3 equal subintervals. So again, this is where the picture is kind of helpful. So the midpoint sum is like now your rectangle is going to be right here at 2.5 and right here at 3.5, 4.5. So the only thing we change really is that now we're approximating this integral still with a delta x of 1, but now it's f of 2.5 plus f of 3.5 plus f of 4.5. Visually, I'm expecting this to be slightly lower than what I got here. So here's another thing about using the function notation instead of the numbers. I can just like quickly change this out. Let's see, 2.5, 3.5, 4.5. So wait, how did I get? I got a bigger answer. Is that possible? Oh yeah, duh, because the first one was lower. I was thinking we did an upper sum for the first one. Okay, yeah, I should have a larger number. So this would round to 4.540. All right, evaluate the Riemann sum for f of x equals square root of x plus 2 on 0 to 9 with 5 equal subintervals. So delta x is 9 minus 0, b minus a, over n, which is 5. So it's 9/5. It doesn't have to be something nice like 1. This one tells me specifically use a right endpoint, round to 3 decimal places. So we are saying the integral from 0 to 9 of square root of x plus 2 dx is approximately, they're all going to have this 9/5 delta x. If we're doing right endpoints, that means if you were graphing this from 0 to 9, your first, and you have 5 subintervals. 1, 2, 3, 4, 5. Okay, so if you have 5 subintervals, your first one is this way. This is at 9/5. This one's at 18/5. 27/5. So you can keep counting on here. So it's going to be f of 9/5 for the first one instead of starting at f of 0. Plus f of 18/5. I'm just adding 9/5 every time. Plus f of 27/5. We're going to have 5 of these. Plus f of 36/5. You could write f of 45/5, but remember you're ending at the end, so that's just f of 9. All right, so I can go back to Desmos here. Change out my f of x. It is the square root of x. The plus 2 is not underneath the square root. Right, and then this is 9/5 times f of 9/5. Oh gosh, I always type this in wrong. Okay, f of 9/5 plus f of 18/5 plus f of 27/5 plus f of 36/5 plus f of 9. 38.243. Remember, we always round to 3 decimal places when we're giving decimal approximations, unless the problem instructs us otherwise. Does the sum represent a lower or upper sum? So I can see this in my picture, but if you haven't sketched the graph yet, you would need to look because right does not always mean upper. This time it is an upper sum because f is increasing. So f is increasing. So this right sum is an upper sum. If your answer is upper sum, that's always an overestimate. Upper sums are overestimates. So it's not always true that right sums are overestimates, but upper sums are always overestimates. All right, given y equals x squared minus 2, approximate the area bounded by the function, the x-axis, x equals 3 and 6. Use a trapezoidal sum using 3 equal subintervals. So I like to sketch a little graph here. Let's see, plug in 3. 9 minus 2 is 7. Let's just say that's there. Plug in 6. 36 minus 2 is 34. This would be some sort of parabola shape. So we're looking at this area into 3 equal subintervals. And we're going with the trapezoidal sum. So let's see, delta x is 6 minus 3 over 3, which is 1. And trapezoidal sum, remember the area of a trapezoid is 1/2 the height, which is delta x, times b1 plus b2, which are actually f of x1, f of x2. All right, so the integral from 3 to 6 of x squared minus 2 dx is approximately, so every trapezoid is going to have a 1/2 times 1. And then you're adding the bases together. So the first trapezoid has these two bases, f of 3 plus f of 4. I'm leaving a gap here because the second trapezoid has f of 4 plus f of 5. So there's 2 of those. The third trapezoid has f of 5 and f of 6. So there's 2 of those. So there should only be 1 on the ends, 1 f of 3, 1 f of 6, but the other ones have 2. Again, I can type this into my calculator. So let's change this to x squared, what was it? Minus 2. All right, and then we have 1/2 f of 3 plus 2 f of 4 plus 2 f of 5 plus f of 6. 57.5 is our approximation. All right, now let's get into that limit definition of Riemann sums. So given this integral, write the limit definition of the Riemann sum, and then write the first 4 terms. So remember, for this, in general, it's this integral is equal to the limit as n approaches infinity of the sum from I equals 1 to n of delta x times f of x sub I. So our job is first to establish what is our expression for delta x and what is our expression for f of x sub I. So an f of x sub I is always f of a plus delta xi. And delta x is always b minus a over n. So start with delta x. It's 3 minus 2 over n, which is 1 over n. Now go with f of x sub I, which is f of a plus delta x times I. A in this problem is 2, so f of 2 plus 1 over n times I. I'm just going to write I over n. I don't always do this, but if you want to, go ahead and plug that in. The function is x squared plus 4, so you would be plugging it in like this. This squared plus 4. Sometimes that helps to get that all out of the way here. And then go ahead and write your limit definition. So the limit as n approaches infinity of the sum from I equals 1 to n of delta x, 1 over n, times f of x sub I. So 2 plus I over n squared plus 4. So this is the limit definition for that integral. They are exactly equal to each other. We're just going to show the first 4 terms. So when you're showing that you're adding some terms together, it's going to drop the sigma notation, but you're going to keep the limit notation because you haven't actually taken the limit of anything, and we're not going to. So 1 over n is in there. And then expand this out. So the first 4 terms just means plug in I equals 1, 2, 3, and 4. Just show what that is. So it's going to be 2 plus 1 over n squared plus 4. That's I equals 1. Plus 2 plus 2 over n squared plus 4. That's I equals 2. Plus 2 plus 3 over n squared plus 4. Plus 2 plus 4 over n squared plus 4. Now you need to show plus ... This goes on forever. We're letting n approach infinity, right? So we're going out to n. I guess I could say show the n term. This goes out to the nth term, and then we would take the limit. I used to teach you how to take limits like this, but I really don't think that we need to do that. So I haven't seen that on the AP test. All right, let's see. D of t is the rate of growth of the deer population in Ohio. Using the table, approximate this integral using a midpoint Riemann sum with 3 equal subintervals, include units. So let's get our delta t. It's 6 minus 0 divided by 3, so 2. So each rectangle is going to span 2 units, 0 to 2, 2 to 4, 4 to 6. Use a midpoint sum, which would be the point that's sitting in the center of each of those rectangles. So it should just be that the integral from 0 to 6 of d of t dt is about equal to, they all have a width of 2. And then I'm just going to use the numbers here. So 3 plus 8 plus 17. What's this? 11 plus 17 is 28 times 2, which feels like 56. And then include units. It's not 56 deer, it's 56,000 deer. And it's not deer per year. Remember, we multiplied years times deer per years. So we're left with deer. Interpret the meaning of this. So here we go. When you multiply deer per year times years, you're going to get the total amount of, I guess I'll call it deer growth, deer population growth, between years 0 to 6, or you could say like in the first 6 years. This was, the population grew by 56,000 deer. All right, here are a couple more Riemann sum problems, formal. So same thing as we did before. So let's establish delta x. It's 5 minus 0 over n, so it's 5 over m. Let's establish f of x sub I. That's f of a, which is 0, plus delta x, 5 over n, times I. And just go ahead and plug it in here. 25 minus, this would just be 5i over n squared. Go ahead and write out the Riemann sum. The limit as n approaches infinity of the sum from I equals 1 to n of delta x times f of x sub I. I don't think there's any reason to square this out, so I'm just going to leave it like that. Write the first 4 terms. So that's still the limit as n approaches infinity. There's no more sigma. We'd have a 5 over n out here. And then start by putting in 1. So if you put in 1, you get 25 minus 5 over n squared. And then add to that 25 minus, put in 2, you get 10 over n squared. Now put in 3, 15 over n squared. Now put in 4, 20 over n squared plus ... Final problem. Start with your delta x. It's 5 minus 3 over n. That's 2 over n. F of x sub I is f of a, which is 3, plus delta x times I. Go ahead and plug that into the equation. That's 1/2 times this quantity squared minus 2. Now it's the limit as n approaches infinity of the sum from I equals 1 to n of delta x times f of x sub I. Now expand out the first 4 terms. Keep the limit notation, drop the sigma, 2 over n. Put in 1 for I, so 1/2 times 3 plus 2 over n squared minus 2. Now put in 2 for I, 1/2 times 3 plus 4 over n squared minus 2. Now put in 3 for I. 1/2 times 3 plus 6 over n squared minus 2 plus 1/2 times 3 plus 8 over n squared minus 2 plus ... We would do that for n terms. Okay, I hope you're starting to see a pattern for how you build these Riemann sums with their limit definition. Come see me in office hours if you need more practice.